Topic 11, Gravitational Fields, Chapter 11.1. Okay, Chapter 11.1, Gravitational Forces. This is what you will learn at the end of this section. You should know this equation. F is equal to G m1 m2 over r squared, where m1 and m2 are the masses of the bodies m1 and m2. G is a constant called the universal gravitational constant. R is the distance between the centers of masses of the two bodies m1 and m2. We will go into detail of this later. Then sketch a graph of gravitational force between two masses at increasing separation. Now if you look at this equation, you can see that when the when the G, m1 and m2 are constant, and if r increases, f decreases. But if r doubles, this will decrease by a factor of 4. For example, if you substitute 2 here, it will become 2 squared, 4. If you double the denominator, then the fraction will decrease by a factor of 4 because it quadruples. Okay, because it's this thing squared. Alright, then the attraction of gravity. You have learned this equation, F is equal to mg. Now the F is actually the weight, so W equals mg. Weight is a gravitational force. You have learned the equation W equals mg, and weight is a gravitational force. So we can also write it as F equals mg. M is the mass, G is the gravitational field strength, also called the acceleration of free fall. On the moon, the gravitational field strength, also called the acceleration of free fall, is about 1.62 newtons per kilogram. The gravitational field strength has the unit newtons per kilogram, and if you write this in base units, you remember the 6 base units: meter, second, kilogram, Kelvin, mole, candela. Okay, so if you break this down into base units and write it and simplify, it will be meters per second squared. Meters per second squared. Okay, this is the gravitational field strength on the moon. Now what we are going to do is find the weight or the gravitational force of the moon on the elephant. What force will a 2-ton elephant feel when it is in the moon's surface gravitational field, which has a strength of 1.62 newtons per kilogram? The mass of the elephant is 2000 kilograms. The gravitational field strength is 1.62 newtons per kilogram or meters per second squared. Then the weight of the elephant on the moon is 3240 newtons. On the earth, the gravitational field strength is 9.81 meters per second squared or 9.81 newtons per kilogram. So 9.81 meters per second squared means that for an object which is falling on the earth, if there was no air resistance, the speed will increase by 9.81 meters per second every second. But on the moon, the speed will increase for a falling object every second by 1.62 meters per second. That's what we mean by 1.62 meters per second squared. Every second, the speed is increasing by 1.62 meters per second. So for example, if you drop an object, drop means the initial velocity is 0. If you drop it after 1 second, the speed will be 1.62 meters per second. After the second, it will be 1.62 times 2. After the third second, it will be 1.62 times 3. Okay. So an elephant has a weight much lesser on the moon compared to that on the earth. And also you can see, if we look at this diagram, you can see it's as if the elephant is floating. Now what happens is, when the elephant jumps, it won't fall back down to the earth or down to the moon right away like on the earth, because the acceleration of free fall, G, on the moon is less. It will take a longer time to fall back onto the moon after it jumps. So when it jumps, it will take a longer time to go to the highest point and to fall back down to the earth, down to the moon. But on the earth, if it jumps, it falls down very quickly. On the moon, it will take a longer time. It goes like that, comes like this. That's what this diagram shows. You will see that the elephant remains in the air for a longer time if it jumps up on the moon. It remains above the moon, not on, there is no air here. It remains above the moon's surface for a longer time if it jumps up on the moon. But this is not the case with the Earth. It falls down quickly because the acceleration of free fall on the Earth is 9.81 meters per second squared. Okay. Here are some more examples that relate gravity. Gravity drives the formation of stars. Here from clouds of gas in the Carina Nebula. We will learn more details about this under astrophysics and cosmology. It's a separate topic which is after this topic. Alright, then we have this equation, the gravitational force F, which we also call W, capital W equals mg. Okay, and you can see this g is acceleration. So we can also write it as F equals ma. Now F equals ma is the Newton's second law equation. This F is always a resultant force. In the case of weight, if it is the weight, now in the case of the elephant, the only force acting on the elephant right now when it is in the air is its weight force. So the resultant force on the elephant is the weight of the elephant. Okay, and always this F is a resultant force, the net force. It is an unbalanced force. Sometimes students confuse this. That's why I always say that this is a resultant force. It is the net force on the body, which is F. So in Newton's second law, F is the net force. Now if you relate it to weight, then W equals mg. But if you use F equals ma, this F is a resultant force. Always it is the resultant, the net force of all the forces acting on a particular body. And this is actually showing you that the weight is actually the resultant force on the example like this, on an example like this. And then if you find A is actually equal to G. Okay. Then we have this other equation. Alright, then we have this equation F is equal to G m1 m2 over r squared. This is the, again this is a gravitational force. This is actually the weight between two bodies. If you consider the Earth and the Moon, there is a gravitational force of attraction between the Earth and the Moon. This is what causes the Moon to orbit the Earth. If there is a force of attraction between two bodies, and if the force is large enough, two things can happen. One is the two objects can be attracted to each other. They come towards each other. The other possibility is that the lighter object orbits the heavy object. The Moon is much lighter compared to the Earth. Therefore, the Moon will orbit the Earth. Similarly, the Sun is much heavier, much more heavier than the Earth. Therefore, the Earth will orbit the Sun. Okay, and another example is if you take an artificial satellite. Now, Moon is a natural satellite. The Moon orbits the Earth. That's why it's called a satellite. Artificial satellite, for example, the Hubble Space Telescope. The Hubble Space Telescope is much lighter than the Earth. So it will orbit the Earth. So always it is the lighter object which orbits the heavy object. There is a force of attraction between those two, and that is the gravitational force of attraction. So if you consider the Moon and the Earth, there is a gravitational force of attraction between those two towards each other, which is also called the weight force. Now the gravitational force of attraction by the Earth on the Moon is towards the Earth. We'll draw a diagram to help you understand this better. Okay, if you look at this diagram, you can see the gravitational force of attraction between the Moon and the Earth. The Moon and the Earth. This is the gravitational force of attraction from the Moon on the Earth. This is the Earth. So this is the gravitational force of attraction by the Moon on the Earth. It is also the weight of the Earth due to the Moon. And this force here is the gravitational force of attraction on the Moon by the Earth. We can also call it the weight of the Moon due to the Earth. and these two forces are towards each other, meaning opposite in direction, and they are the same size. This is a Newton's third law pair. If you remember, a pair of forces, to be a Newton's third law pair, has to meet 6 criteria. They have to be the same size, they have to be in opposite directions, they have to act on different bodies, they have to have the same line of action. Okay, so you can see over here they have the same line of action. They have to act for the same period of time. Okay, if you're not familiar, you can watch a video on the Newton's third law pairs. There's a separate video that I've uploaded explaining Newton's third law. You can watch that. And this R, if you look at the formula, there was a R there in the formula. Alright, and then R was the distance between the centers of masses of the two objects. You can see over here, this R here is the same as the simple R that you saw over here. Remember, it is from the center of this to the center of the other one. It's very important that you understand this equation, F is equal to G m1 m2 over R squared, because you will have a lot of questions where you have to use this equation again and again and again. So make sure you really understand this equation. G is the universal gravitational constant. It is a constant for the whole universe. The value of that is 6.67 into 10 to the power of minus 11 newtons meter squared per kilogram squared. And if you forget the unit of this, you can work it out from the units of the other quantities. Now if you make G the subject of this equation, you will see that the unit of G will be Newton. Now when you move the m1 m2 to this side, R squared will go there, so it will be Newton meter squared. Kilogram times kilogram is kilogram squared, but it is in the denominator. So kilogram squared to the kilogram to the power minus 2. Okay, so this is the unit of the universal gravitational constant, and it has this value. It is the same for anywhere in the universe. So make sure you understand the equation, and you should be able to use it because, like I mentioned before, you will be using it again and again. Let's go through an example to help you understand this equation better. And this F is the gravitational force of attraction between the two bodies. It is equal in magnitude, opposite in direction, and it's a Newton's third law pair. Okay, so the F was this force F here. It's the same as this force F here. It's equal in size. So in this equation, F equals G m1 m2 over R squared. F is this force over here, and also it's this force over here. Okay, let's go through the example. What force will exist between two neutrons in the Crab nebula which are separated by a distance of 2 meters? Two neutrons separated by a distance of 2 meters. So we assume that the distance between the centers of masses of the two neutrons is 2 meters. And 2 meters is a very large distance compared to the radius of the neutron. Okay, so here when they say 2 meters, we assume it's from the center of one neutron to the center of the other neutron. Now we'll use this equation. F is equal to G m1 m2 over R squared. G, I told you, is a constant for the whole universe. We saw that earlier. It is equal to this value. So we'll substitute that for G. Now m1 and m2 are the masses of the two neutrons. Each neutron has the same mass as another neutron because it's still a neutron. You don't need to remember the mass of a neutron. It will be given to you in the data sheet. The value of that is 1.67 into 10 to the power minus 27. The mass of a neutron is approximately equal to the mass of a proton. Now since we have two neutrons, m1 and m2 will have the same size. So here, that's why they write this here once, and the same thing again over here. The mass of the first neutron, mass of the second neutron, divided by R squared is the distance between those two, that is 2 meters, so 2 squared. Remember to square this. It's F is equal to G m1 m2 over R squared. Then you will get 4.65 into 10 to the power minus 65 newtons. So this is how you use this equation. So make sure you are very familiar with the quantities in the equation. Part B, how quickly will each accelerate towards the other, ignoring the effects of all other particles? Now we assume that only these two neutrons are there. There are no other particles, we assume, because if there are other particles, what will happen is there will be a gravitational force of attraction exerted on these neutrons by the other particles also. So here in part B we assume there are no other particles. Now what will happen is you have the two neutrons, they are exerting a gravitational force of attraction between each other, and what can happen is they will come towards each other because it's a gravitational force of attraction. Since it's an attraction, the two neutrons will be coming towards each other, and we are supposed to find how quickly they will come towards each other, which means we are supposed to find the acceleration of a neutron. How quickly will each accelerate towards the other? We can use the formula F equals ma. The acceleration is then F over m. We already found the resultant force. Now we can consider one neutron. The force on either neutron is the same size. Okay, so the two neutrons are two different bodies. There is a force F, which is 4.65 into 10 to the power minus 65 newtons exerted by one neutron on the other neutron. So if you consider one neutron, the resultant force on a certain neutron is 4.65 into 10 to the power minus 65 newtons. And I told you in this equation F is equal to ma, the Newton's second law equation, F is a resultant force. F is a resultant force. Okay, so the resultant force on the neutron is this. The mass of the neutron will be given to you in the data sheet. That is already, we saw that in the previous part of the question also. 1.67 into 10 to the power minus 27. Substitute those quantities into the equation, then you will get the acceleration of each neutron towards the other neutron. That is 2.78 into 10 to the power minus 38 meters per second squared. You can see it's a very small number, so it's coming towards it very slowly. Okay, part C. Why is it difficult to calculate how long they would take to reach each other? Okay, so we have the acceleration and we know the distance between the two. They are asking why is it difficult to calculate. Okay, so the acceleration is inversely proportional to the square of the distance between them. Therefore, the acceleration is constantly increasing as they get closer together. Our usual equations of motion require constant acceleration. You have learned the SUVAT equation, SUVAT.
Yeah.
Okay, V equals U plus AT, S is equal to UT plus half AT squared, V squared equals U squared plus 2AX. Those were the SUVAT equations. For those equations, the acceleration had to be constant. But in this question, what happens is the acceleration is inversely proportional to the square of the distance between them. You can see F is equal to ma. Now, if you write, instead of F here, if you write ma, then you will see that the acceleration is inversely proportional to the square of the distance between them. That's why the acceleration is constantly increasing as they get closer together. When r decreases, when this quantity here decreases, the acceleration increases. F is equal to ma. So instead of writing F here, you can write ma there. Okay, that's why we can't calculate it using the equations of motion that we learned, because those equations require the acceleration to be constant. Alright, then there is another equation, V equals 2 pi r over t. Now I will tell you how you get this equation. They have also shown you something more. Okay, first I will tell you how to get this equation. Now this equation you have learned, velocity is equal to displacement divided by time, or we can say speed is equal to distance divided by time. Okay, so we learned that equation, speed is equal to distance divided by time. Now if you consider a circle, orbit is a circle. When the moon orbits the earth, or when the earth orbits the sun, it is going in a circle. When it goes in a circle, the circumference of that circle is given by 2 pi r. So the distance therefore is 2 pi r. For an object that is orbiting, it's going around in a circle, it's going along the circumference of the circle, the orbit is a circle, so that distance is 2 pi r. Then the time is capital T, because when it goes all the way around, that is the period. If you remember the definition of frequency, if you remember the definition of period is the time taken for one complete wave, one complete oscillation, one complete cycle, one complete Orbit also we can say, one complete revolution. So when the object goes one whole round, one whole orbit, the time for that is the period, capital T. Okay, so it travels a distance which is equal to the circumference of the circle when it goes one orbit, that is 2 pi r, and when it completes one orbit, the period is the time taken for one complete orbit. We use capital T for period. So that's how we get this. The velocity, the speed is distance over time. The distance is the circumference 2 pi r. The time is the time for one complete orbit, which we write as capital T. That's how you get this equation. So v is the speed. Speed is distance over time. The distance is the circumference of the circle, the orbit, and the t is the time taken for one complete orbit, which is the period. That's why we use capital T. If we use simple t, it can mean any time. But when we use capital T, it means the time for one complete orbit. Okay, so we have 2 pi r. Okay, r, now in this case the speed of the moon comes from the time it takes to orbit. So we are finding the orbital speed of the moon. Alright, so for that we will need the radius of orbit of the moon. That is the distance from the center of the earth to the center of the moon, r. And then t is the time taken for the moon to complete one orbit around the earth. This is related to what we have here. So we can, I think, yeah, it's given here. See, the period, the time period of the moon's orbit around the earth is 27.3 days or 2.36 into 10 to the power 6 seconds. This is in SI units. And you can see that is what is substituted over here, 2.36 into 10 to the power 6. Then the radius r, we will check that also. The average orbital radius for the moon is 384,000 kilometers, or in SI units it's 3.84 into 10 to the power 8 meters. That is also given. So that is what we substituted here. Now we get the orbital speed. So the moon travels at a speed of 1020 meters every second in that orbit. It can go at this speed because it's in a vacuum. There is no air resistance. So in 1 second it can travel at this speed, this much distance. So about 1 kilometer every second the moon travels. Okay, so let's go to the beginning of this one. Now you have this question is actually relating to the earth and the moon, something like this. We are going to find this force F. Okay, so not find it, we are going to use that equation. Now the moon is orbiting the earth, so it's a circular motion. You have learned that anything that is moving in a circle will have a centripetal force. This centripetal force is directed towards the center of the circle in which the object is moving. And the centripetal force is not a force by itself. It takes the form of other forces. Now in the case of the earth and the moon, the centripetal force is the gravitational force of the moon on the earth on the moon, the weight of the moon due to the earth. Okay, so if you look at this diagram, this is the moon, it's orbiting the earth like that. Okay, so this force is the centripetal force on the moon, which is causing it to orbit the earth. Because it's moving in a circle around the earth, it's orbiting the earth, there is a resultant force on it. This resultant force is what we call the centripetal force. Always remember, centripetal force is a resultant force and it's not a force by itself. It takes the form of other forces. Now in the case of the earth and the moon, the centripetal force is the gravitational force. If you consider the nucleus and the electron, for example, if you consider the hydrogen atom, an electron is orbiting the nucleus of the proton of the hydrogen atom. So there you have a electrostatic force of attraction. Therefore the centripetal force there between the proton of the hydrogen atom and the electron of the hydrogen atom is the electrostatic force of attraction. So their centripetal force is electrostatic force of attraction. Here the centripetal force is the gravitational force of attraction. Another example is let's say you have some stone or something tied to the end of a thread and you swirl it. Then what will happen? There is again the stone, you have the stone tied to one end of the thread and you're holding the other end and you're making the stone move in a circle, you're swirling it. Then what will happen is because the stone is moving in a circle, anything moving in a circle will have a centripetal force acting on it. This centripetal force is a resultant force, and it is always directed towards the center of the circle in which the object is moving. So there, the force on the stone is the tension in the string. If the tension was not there, the stone can't move in a circle. Okay, so for details of this, there is another video that I've uploaded about centripetal motion. You can watch that video about centripetal motion, that is a circular motion. Okay, so there I'm explaining the centripetal force and all of that. Now, centripetal force was given by F is equal to mv squared over r. This equation. Do you remember this was the equation for centripetal force? F is equal to ma, but a is the centripetal acceleration. Always the acceleration is directed in the direction of the resultant force. Acceleration and resultant force are in the same direction. So the centripetal force and the centripetal acceleration are in the same direction. It is the resultant force which produces the acceleration. So centripetal force produces the centripetal acceleration, and the centripetal acceleration is given by v squared over r. Okay, if you are not familiar with that, you have to review circular motion. Okay, so we have F equals ma, and since this is the centripetal force F here, it is the centripetal acceleration is given by v squared over r. So F equals ma, a is what, v squared over r. So this v squared over r is the centripetal acceleration. So we substitute that for here. Now mass of moon, m for moon, this is the mass of the moon. Now the centripetal force is on the moon because it is the moon that is orbiting the earth. Then we have, so this is the equation for centripetal force. This is the equation for the gravitational force. Now in this case, what is happening is the gravitational force is the centripetal force. So we can equate the two equations. We can set these two equal to each other like this. This is the mass of the earth, this is the mass of the moon. Now what happens is the mass of the moon cancels out. So we get gme, g times the mass of the earth divided by r squared equals v squared over r. This is the orbital speed of the moon. How fast the moon orbits the earth. Then we simplify. Here we have r squared, here r, then we get this. And then we are making this the subject of the equation. Let's say we want to find the mass of the earth. So this is the equation. Now if you remember, we already found the orbital speed of the moon. We already found v. R was already given. G also we know it's a universal constant, universal gravitational constant. So using this we can find the mass of the earth. Substitute those into this equation, R, V and G, then you will get this one. Okay, everything was substituted in SI unit, so you get your answer also in SI unit. So weighing the earth can be done by observing the moon. That's what we did just now. Now it's very important that you answer all these questions. Check the solutions or check the answers which are there. If you Google, you can find the document which has the answers. It also comes, I think, with the CD of the book. It's very important that you answer these questions. Then whatever in this book that is in red like this is very important. You can see a gravitational field is a region of space-time which is curved. This curvature will cause particles to experience an accelerating force. In the exam papers, they can ask you to write down what is gravitational field. Whatever is given like this under key definitions, in the exam paper they can ask you to write it down. That's why you have to memorize this with understanding. Okay, so that when they ask you to define gravitational field, if you write this, you will get the full marks. It is better if you memorize it with understanding rather than trying to write it in your own words, because in definitions they look for keywords. Now if you write it in your own words and if you are missing certain keywords, you would not get the full marks for the answer. That's why we say memorize it with understanding, so you have all the keywords that are required for the answer. Okay, so we'll continue now. Now the next part, 11.1.2.